All right, good morning. I guess good morning, everyone. Any questions? Y'all doing all right? How's the 7-1 homework? Everything go okay?
Went all right for me.
Yeah. Anyone have questions over anything? Nope. All right, let's get down to business then. We're going to cover 7.2 and 7.3 today. And the next time 7.4 and 7.5. We'll see how things go time-wise. Hopefully, I'm a little ambitious there, but we'll see how it goes. Before we do the 7.2 and 7.3, I want to do one more problem out of 7.1, where we're finding the area between two curves. And you'll see after we do it why I'm doing this. All right, so here's the question. I want us to find the formula for the area of a circle of radius r. Okay. So we should all know the answer to this already, right? If somebody gives us a circle with a radius of r, we all know that the area of this is pi r squared, right? We know that, but where did that come from? Right? So where is this formula actually coming from? And so that's what I want us to do, is I want us to establish that formula. All right, so this is a pretty big deal, right? We're going to somehow use what we've learned in this class to establish that the area of a circle is pi r squared. So the way I'm going to go about this is I'm first going to start by reminding you that if you have a circle that is centered at the origin, gosh, my circle's terrible. Okay, and it has a radius of r, that the equation of that circle is x squared plus y squared equals r squared. Right? That would probably be a college algebra / pre-calculus topic. It comes from a more general formula. There's a formula that looks like this: x minus h squared plus y minus k squared equals r squared. And that gives you the equation of a circle that's centered at HK. So if you just give me a circle, put the center of it right here at the point HK, and give it a radius of r, then that's the formula for it, or that's the equation of it. All right. So with this equation, right, this one right here, that is the equation of a circle that is centered at the origin of radius r. And I would like for us to find the area of it. Okay. So the way I'm going to do this is I'm going to take this equation and I'm going to solve it for y first. Okay. So if I move the x squared to the other side, right, and then take the square root, I have to do plus or minus square root of r squared minus x squared. That gives me the equation solved for y, which really means we have two different functions. We have a positive square root thing and we have a negative. The positive part of this would draw the top part of the circle, and the negative part would draw the bottom half of the circle, because we should all be comfortable with the idea that a circle is not a function of x, fails the vertical line test. And a circle is not a function of y because it fails the horizontal line test. We talked about that last class. So in order to draw a circle solving for y, you have to actually draw two functions, a top and a bottom, separately. Does that make sense, everyone? So here's how I'm going to go about this. I'm going to try and find the area of this circle by just looking at the first quadrant and only looking at the area underneath this corner piece of the top function. All right. So if I were to draw a rectangle in here, no matter where I draw that rectangle, the top function is what? What would the top function be?
That the y equals plus the square root of r squared minus x squared.
Yes, that would be y equals the positive square root of r squared minus x squared, right? And what would the bottom function be?
Y
What would the
equals 0.
bottom- It's always just the ground, right?
Yeah.
Which is just, yeah, y equals 0. So from what we learned last class, the area, right, of that blue region should be the integral. All right, now think about your limits of integration. We're going to be doing vertical rectangles here. So we want to start here at the origin, right, at 0. And we want to stop where? Where do we actually stop this integration?
At R?
At R, yeah, exactly, at the radius of the circle, right? That's how far out you're going to go. So you're going to go the integral from 0 to R. Now keep in mind, R is a constant here, right? R is a fixed number. Whatever the radius is, it's given to us. It's not a variable, it's fixed. And then we're going to do the top function, which is the square root of r squared minus x squared, minus the bottom function, which is 0 dx. That makes sense, everyone? Yeah. Which is just integral 0 to r. I don't need the 0 in there. R squared minus x squared dx. And for this, I'm going to find the antiderivative of this, I'm going to use trig sub because I have a square root here, right? And I have something that looks like square root of a squared minus x squared, right? So for us, when we do the trig sub, the r is the a in the trig sub. And so I just need to know what trig sub I'm going to use here. Well, with that form, I use x equals a sine theta. So for us, it'll be r sine theta. And then dx will be the derivative of that, which is just r cosine theta d theta. And then the square root piece turns into r cosine theta. I'm not going to go through all that again because that's all trig sub we've done in the past, right? You following me? So this becomes, let me see, I'm going to do this new integral over here. I'm going to do it without the limits of integration. I'm just going to do a general antiderivative. I'm going to substitute the square root, becomes r cosine theta times dx, which is the r cosine theta d theta. Y'all understand all I've done is rewritten this integral, replace the square root in the dx with my trig sub? Yeah. Let's pull an r squared out because it's a constant. I'll have cosine squared theta d theta. And when I see cosine squared, I automatically think I'm going to use the power reducing formula or the half angle identity. I'm going to rewrite that as 1/2 1 plus cosine 2 theta. We did that a lot in the past, so that should be no surprise to you. I'm going to pull the half out, half r squared integral of 1 plus cosine 2 theta d theta. And let's do an antiderivative. 1/2 r squared. Okay, antiderivative of 1 is theta. Antiderivative of cosine 2 theta is going to be plus 1/2 sine 2 theta. Have we done that enough where y'all are like, you understand what I'm doing? I'm like, we've done this. Okay.
Yes.
Okay, we need to get everything back in terms of x. So this is where I'd use my reference triangle. This right here, x was equal to r sine theta. Divide both sides by r. So sine theta is x over r. So if this is theta, sine is opposite over hypotenuse. This side is r squared minus x squared under a root. And we still have more to do. I know I'm moving fast through this, but okay, theta, I take the inverse sine on both sides here. So I get inverse sine of x over r. And then this one, remember, this is where we had to use that identity that sine 2 theta is 2 sine theta cosine theta. And the 2 and the half go away. So I'm going to have plus here. I need sine theta, which is x over r, times cosine theta, which is the adjacent over the hypotenuse. Okay, there it is. That's the antiderivative, right? Y'all good? Y'all with me? Y'all with me? So that's going to go, let me copy this. That's my antiderivative. So I'm back up here now. This up here becomes this, but evaluated at the two endpoints, 0 and R. Right? 0 and R. So let's start by plugging in R first. And remember, we're plugging in R for what variable? R is going to get plugged in for what? For
X.
X, right? For X, everyone, right? So let's plug it in. We have 1/2 R squared. Okay. If I plug in R right here, R over R is 1, right? R over R is 1. So I get inverse sine of 1 plus, okay, now check this out. If I plug in R right here to this X squared, it becomes R squared minus R squared, which is 0, right?
0.
And that kills everything off here, doesn't it? Because I have a 0 on top. And so it kills everything. I get 0 there. And then I have to plug 0 in. So I'll have 1/2 R squared. Now let's plug in 0. If I plug in 0 for X here, I get inverse sine of 0 plus, and then check this out. If I plug 0 into that X right there, I get 0 on top there, and it kills all of this off again. So I get 0 there. I forgot a second parenthesis right there. Okay, any questions? All right, let's see what this is. We have 1/2 R squared. Okay, now the inverse sine of 1 is basically saying where on the unit circle is sine, at what angle is sine going to give you 1? So at what angle is sine 1?
Pi over 2.
Pi over 2, right? So this is going to be pi over 2 plus nothing, right? And then we have minus, and then over here, 1/2 R squared, and then times inverse sine of 0. So at what angle is sine 0?
0.
Well, 0. So that's 0, which kills everything off there. So your final answer over here is, let's see, 1/2 times R squared times pi over 2. Let's bring the pi over 2 up front with the half. We get pi over 4 times R squared. That's our answer. Right?
Of that
Well,
coordinate.
yeah, that's just the top right corner, right? So if we want the area of the whole circle, we need to multiply that answer times 4. So if I were to take this and multiply it times 4, you get pi R squared. There it is. It's cool, right? Now you can see how you can use calculus to derive the area of the circle.
Good Lord.
I wanted to just show you that because as we proceed, I'm going to show you that, how to find the area of a circle. I'm going to show you how to find the volume of a sphere. I'm going to show you how to find the surface area of a sphere. All those formulas that we have, we're going to derive them ourselves. But I needed to go back because I forgot I hadn't shown y'all this. At least I want to show you how to find the area of a circle, okay, before we do anything else. Okay, that's it. We're moving on. Questions? All right, so today we are talking about 7.2. Let me bring up my notes here. A few little things we need to get clear before we do anything is some geometric stuff, okay, three-dimensional stuff. If I were to give you a box, okay, something shaped like a box, we actually have a technical name for this. It's called a parallel pipette. Okay, so you take a shoebox, all right, that's called a parallel pipette. The volume of that is length times width times height. Everyone here should be comfortable with that idea, right? Just do your length times your width times your height, and that'll give you the volume of this three-dimensional object. Now, if you take a right cylinder, okay, the volume of a right cylinder is pi r squared times h. That's also something that you should be familiar with from the past. And the way I think about a cylinder is this. The volume of this is pi r squared times h. The height here is h. And if you look at just this top edge or the top of the surface, that's a circle. And we know the area of that's pi r squared, right? Pi r squared is this. So the formula for this is that you're taking really like the area of the circle and you're multiplying it times like the depth of the cylinder. And that gives you the volume. Does it make sense to you that it should be that? It's just that surface area on top multiplied by the depth, and that gives you the total volume. Good? Those two geometric objects. Okay, the other thing we need to know is how to find the volume of a washer, which is basically a cylinder that has a cylinder cut out of the center of it. So I'm going to do a drawing here for us. So we have this big cylinder, right? Like this. Let's say that the radius of this one, we'll call it R out, okay? And then this right here, we'll call that H. Then the volume of this is going to be pi r out squared times H, right? Then what we want to do is we want to come in here and we want to cut out a cylinder inside, okay? Now this smaller cylinder is going to have its own radius, which we will call R in. And so the volume of this guy is pi r in squared times the same height, because they both have the same thickness of the washer. So if I want to know the volume of the whole thing with the center cut out, I'm just going to take this one and subtract from it this one, right? Take the volume of the big one, subtract the volume of the small one. That's what I have written here. Pi r out squared times h minus pi r in squared times h. And then what I do is I factor out a pi. They both have a pi. So I pull a pi out. There it is. And they both have an h. So I pull the h out, but I put the h in the back. I could have put it in the front like this, pi h, r out squared minus r in squared. I could have written it that way, but I put the h on the back side, and you'll see why I did that later, okay? Understand? Okay, so remember these formulas. We're going to need this in a little while. The last one we need is the volume of what's called a cylindrical shell, okay? And I think I'm going to wait on this one. I'm going to wait till we get to it, all right? It's basically the same idea. It's like a cylinder, but it's really tall, okay? And it has a very thin wall to it, as opposed to a washer, which is very flat, right? And then has kind of a thicker wall. This is called a washer. This is called a shell. Again, let's hold off on the shell. We'll talk about it in a minute.
Why would these need different formulas?
You'll see. You'll see.
Okay.
That's why I want to wait. That's why I want to wait. I mean, you could set it up the same way, but we're going to set this other one up a little different. All right. Okay. Let's get into today's stuff. This is just stuff we need to know before we can proceed. So I'm going to bring up a visual for this. Let me see. Yeah. All right. So last class, the whole idea was that if I gave you two functions, a top function, a bottom function, or if they were functions of y, we could have a right function, a left function, we should be able to find the area of the region between them, between 2 points, right? Like for here, it would be from A to B. So the area of this, right? The area of that would be the integral from A to B of that top function f of x minus the bottom function g of x dx. Yes? We know how to do that, or we studied that already. Here's what we're gonna do today, all right? And this is always like, I love this, okay? What we're gonna do today is this. Take that same area, okay, that same region, but what I'd like for you to do is take it and look at this as being like the whole, like this is a sheet of paper sitting in three-dimensional space. And I want you to take that region, I want you to rotate it around the x-axis. Okay, rotate that around the x-axis. And what would you have if you did that? Like, what would you be looking at?
A
What would it
lumpy
look like?
cylinder.
Something, it would look weird, right? Okay, so see, when I was in Cal 2, we didn't have computers like this. So my professor was trying to draw this on the board. Here's what we're gonna do. We're gonna take this sheet of paper and we're gonna break it into three-dimensional space, okay? All right. And now what we're gonna do is we're gonna take it and we're going to rotate this around, okay? There we go. Sorry, I forgot to click on this. We're gonna rotate this around the x-axis and create a solid object out of it. Now, I'm going to make it somewhat transparent so that you can kind of see that the inside, there's a hole in there, but the hole is not straight, right? Because it follows the curvature of the bottom curve, right? The question is, what is the volume of that? How much space does that thing take up? That's what we want to do. Now that might appear at first to be like, wow, this is going to be extremely difficult to do, right? Like, how do you even begin to try and calculate a volume like that? Does that make sense? That it seems hard, but do you see the visual of what I did though? Does everyone see what I've done? Like visually, you have any issues with it?
No, I understand the shape.
Okay.
I could find the volume of this if I had it in real life. You just dunk it in water,
Yeah, dunking in water, exactly.
you know, displacement.
What we want to do is we want to see, can by just knowing the two functions, right? We have to go back to what we started with. If we just know the two functions, right? And we know the A and the B, from that, can I give you the volume of the object that you would create if you've rotated this region around the x-axis? Can we do it, right? Okay, so that's the task. That's the task. Let's see how we're going to do it. So I have another animation here. So let's go back to this picture. So what we were doing before is we were saying, oh, you know, if we wanted to find the area, we would just pick some arbitrary rectangle in here, right? And what we did was we found a formula for this, didn't we? Think about area right now, area, not volume. Don't worry about rotating anything. Just when we were trying to do area, we said, okay, we're going to find the area of that one rectangle. And we said, okay, well, this is just the that top one, f of x minus the bottom one, right? And we said that the width of it was dx. And so the area of that little sliver, right? The area of that little sliver is just your f of x minus your g of x, and then multiply times the dx. That's basically like your width times your height. And that would give you the area of that one little sliver. And then we want to add them all up, right? So how do we add them up? What do we use? The integral, right? The integral is the thing that adds them all up. And you just put the formula in here. You put the f of x minus g of x dx. That's going to give you what you're adding up. You're adding up all those little areas. And you're going to start at A and end at B, right? Start at A. So that means you're going to start with your rectangle over here, way on the left side. And then you integrate. So you start adding them up. Infinitely many of them, right? Remember that the integral is a limit of a sum, the Riemann sum. So we add them up all the way till we get to B. Right? That's what we did. Okay, that's not what we're doing today. But I just want you to remind you that this integral is a way of adding a bunch of things up, and that what's in the integral is just the thing you're trying to add, right? You're just trying to add, in this case, areas together. here's how we're going to address this. We're going to take this same picture. Again, I'm going to break it into 3-dimensional space. And instead of trying to look at the whole object as one big object, I'm going to cut it into slices. So I'm going to take just that rectangle and rotate just that rectangle around the x-axis. Okay, just that. And if I look at that, that is a washer, isn't it? It is a washer. And if I move the rectangle, of course, the shape of the washer is going to change, right? Depending on where I am. But if I can come up with a formula, right? If I can come up with a formula, a general formula for a slice, a washer, right? Just one of the washers, then I can use the integral to add them all up. But I need my formula to be general, so that as I move from left to right, the formula, accounts for all the differences in the f and the g function. All right. Does that make sense what I'm trying to do here? If I can do this, if I can do it correctly, then I will in fact get them all together, and then I will have the volume of the object. Okay. So let's look at how we're gonna do this formally. Where am I? I forgot to bring up a file. Hold on, where is it? Give me a second. I want to show this to you. In our course homepage here. Under files, where's files here? Under course notes, 7.2 and 3 volume summary. You should have this thing handy and ready for you on the test for sure. This is what I'm about to refer to right now. Okay, this sheet right here. So let me bring it up. All right, see if you can follow this. So what we're trying to do is we're trying to find what's called a solid of revolution. Okay, it's a revolution, right? You're taking a region and you're going to revolve it around the x-axis. So when we do this, we are going to set it. Let me come back to this page. I'm going to do the most general, generic one first, or the easy one first. Let's say we have some function on top, f. And let's say we have some other function on the bottom, g. And let's say we're going to start it here at a and end it, let's say, right here at b. And what we're going to try and do is take this region and rotate this around the x-axis. Okay. So I start by taking an arbitrary rectangle. This is arbitrary, it can be anywhere. Okay. And then to the side, I'm going to draw that rectangle again. I told y'all last class, get used to doing this because you'll need it later. Well, later is today. The top function is f, right? The bottom function is g. The x-axis is right here. And I'm rotating it around the x-axis, right? So to show you I'm rotating around the x-axis, I'm going to draw this like arrow, this circular arrow like that. And that's telling you that what I'm going to do is I'm going to take this rectangle and I'm going to try and rotate it around that x-axis. Now, when I do that, this is going to be the tricky part for you. When you do that, you're going to have to see that you have this washer. I'm going to draw it to the side. And the washer would look like this. Let's see, the inside would have a hollow piece to it like that. If you want, you can even put your little rectangle in here to kind of see that rectangle gets rotated around. I realize you're trying to draw something 3-dimensionally on a flat sheet of paper. It's probably going to take you some time to get decent with it. Even my picture's not that great, okay? Your axis of rotation is right in here, right? You're rotating around this axis here. So what is the volume of that, right? That would be the question. Can you come up with a formula for the volume of that one little piece? Just that one little piece. Remember, the bottom function is the blue one. The top one is the red one, right? So if we go back to the note I started class with this, where is it here? Right here, this volume of the washer. I had this version right here. If I slap that here, the volume of this piece should be pi times the outer radius squared minus the inner radius squared times h. Well, what's the outer radius for us?
And that just going to be F.
It should be the f function. Isn't that the distance from here to the axis of rotation? From there to there, that's our f of x function. And that is the r out, right? And then the r in would be the g function, right? And what about the height? What's the height of this cylinder? So how
dx.
thick is it? Yeah, just like before, we had the rectangle and the width was dx. That's dx right there. Right, that's your h. Which means that the volume of this one sliver, let me move this down here. Sorry, it's getting messy. The volume of this one sliver should be pi, parentheses, the outer radius squared. That means you take the function f and square it, then minus the inner radius, which is the g function, squared, and then times dx, which is your h. And that is the volume of just that one little washer, right? It's the volume of one of them. Any questions on that? So that's the volume of one, and I want to now add them all up, right? So how do we add up all these washers together?
You
We
integrate
bring
it
in the integral,
from
right?
A to B.
Bring it in. And we're going to go from A to B, which means our washers are going to start at the left end point at A, and we're going to slide the washers across, right? And what are we doing? We're doing pi. Then we're doing the f of x, whatever that was, squared minus the g of x, whatever that is, squared, and then dx. And that is it. That is it.
So,
Was there a question?
I had a question, sir. How would you take the
Yes.
volume of like sine or cosine? Would it be the same thing?
Yeah. You mean if you want to take the sine function and rotate around the x-axis?
Yes, because there wouldn't be an inner, like, what is it? The in.
Yeah, there wouldn't be a,
Right.
your bottom function would be 0, right? So when you rotated it, it would be solid. There wouldn't be a hole in the middle. Right? It would look kind of like a football. If you just took like one arc of sine like that and rotate that around the x-axis, it would be almost like a football, right? Okay. So let me run through this again, because there's something very subtle here that I want you to understand. This formula is nice, okay? This is nice, but this is not the way that I want you to think about it. It's not always going to be just square your f function, take away your g function squared. It's not always going to be that. And you'll see why in a minute. So let me go through this again verbally. We're trying to take this region bounded by f and g, right? On this interval AB. We're trying to rotate it around the x-axis. So what we do is we draw the rectangle, we find the upper bound of the rectangle, the lower bound of the rectangle, we draw our axis of rotation. Okay, pay attention to these words that are about to come out of my mouth. R out R out is the distance from the outer edge of the rectangle to the axis of rotation. Okay, R out is the distance from the outer edge of the rectangle to your axis of rotation. In this particular case, it's the F function, right? Because that's the height of F is how high up that top edge is. I like to look at it like if you were a person standing here on the x-axis, you see that red dot? Imagine that's the top of your head. You're looking straight, you know, we're looking down. I can see the top of your head. You're looking out and you can see the edge of the rectangle out there. You're trying to measure that distance. That's R out. The distance from the outer edge of the rectangle to the axis of rotation. R in is the distance from the axis of rotation to the inner edge of the rectangle. Okay. Once you know what R out and what R in are, everything's simple because you just plug it into the formula. So let me bring up those notes I was talking to you about.
So it's the same general dilemma as the previous lesson where it's figure out which one's on top, and then using that, it's just plug and play.
Kind of. Right now, I'm only asking you to rotate it around the x-axis, right?
Yeah. You could
But there's nothing that's stopping me from asking you to rotate it around a different line.
Yeah, you could pick any arbitrary line, I suppose.
That's right. I could pick an arbitrary line. And then it's not just F and it's not just G. That's why I'm trying to get you to understand it in the sense of R out will always be the distance from the axis of rotation to the outer edge. R in will be the distance from the axis of rotation to the inner edge. Whatever it turns out to be, that's what we need to find. Okay, so let me before I give you that, let me take this same picture. Let me take the same picture. I think I'm going to try and illustrate this now. What if I gave you that same picture, but instead of me asking you to rotate it around the x-axis, what if I asked you to rotate it around this line, this horizontal line down here? Okay, and I'm just going to say that that's, let's say that's -3 down there. I want you to rotate it around here. Okay. So what's going to happen? Let's see. We have the the rectangle over here. The top edge is the red. The bottom edge is the blue, right? We have the x-axis here. And we have our axis of rotation way down here. So if we rotate that, what is this going to look like compared to this one? I mean, are they both going to be washers?
Yeah, but it'll be a much larger washer.
Yeah, it's going to be much bigger, isn't it? Like it's going to have a way bigger hole in the middle. Do y'all see? Do y'all understand that? Like, because this axis of rotation is much closer than this one is. So if I rotate this, let's take that rectangle, let's rotate it around here. That means it's going to look more like, boy, it's going to be real big. It's going to come way down here and come back up. It's not a good picture, okay? See, there's a lot more space in between here because our axis of rotation was so far away than here it was much smaller, which means we're going to have a different volume, right? These won't have the same volume. So if I'm sitting here trying to figure out what my R out and my R in is, right? Because I'm still going to use this formula. That's still the volume of any washer. My R out is the distance from the axis of rotation to the outer edge. This from here to here, that's R out. And this from here to here is R in. Right? But is R out equal to F of X?
Would it be F of X minus whatever the value of that axis of rotation is?
Yeah, this is F, right? That's F.
Mhm.
From the x-axis to there is F, or F of X. And then this right here is G, right? That's your G function. but we're trying to go from here all the way down to here. We know that this distance is 3 as an absolute value, isn't it? And this distance is also 3. So if I wanted to know R out would be the F function plus 3. And the R in would be the G function plus 3. See, the 3 accounts for that additional shifting of that axis of rotation. And then once you have that, you just plug them in. Let me show you a different picture. We're going to do some examples. I just want to show you a different picture. Where's my other one? So here is a visual representation of the same region. Okay, so this is the same. We're looking at the same region, 3 different perspectives. This one right here, we're going to rotate around the x-axis. This one, we're going to rotate around a line that's below the region. And here we're going to rotate around a line that's above the region. And I want you to see how all of these are different. You see that? Depending on where our axis of rotation is, it changes the shape of the washer, which changes the volume of the washer, which changes the volume of the whole thing. So your axis of rotation is critically important. If we were to do all of them, look at the objects, kind of slowing my computer down here. That's what the 3 solid objects would look like. They all have very different volumes, right? The volume of that is going to be different than the volume of that, and it's going to be different than the volume of that. Okay. Let's do an example. I think we need to just at least try something. All right. Do y'all understand the geometric picture, at least, like what we're trying to do? Okay, so let's do a specific one here. Let's take if f of x equals, let's go x squared, and g of x equals the square root of x. All right. Find volume of solid if region bounded by F and G is rotated about colon. We're going to do a couple of them. First, we're going to rotate it around the x-axis. Then we're going to rotate it around the line y equals -5. And then we're going to rotate it around the line y equals 5. And then we'll do one more around the line y equals 1. So we have 4 problems. We're going to find the volume of 4 different solids. Each one of them is generated by taking the region bounded by these 2 curves and rotating around one of these 4 lines. Notice these are all horizontal lines, right? They're all horizontal, right? Okay, let's do it. Start with the picture. X squared. That's F, right? Square root of X. That's G. The region bounded between the 2 is obvious, I hope. I also hope it's obvious where they intersect. You could set them equal to one another, but I would trust that you could get the two solutions 0 and 1, right? We want to take that and we want to rotate that around 4 different axes. We good to go? Can we proceed? All right, now I'm going to have the fortune of being able to copy and paste here. Let's do part A. I want to rotate it around the x-axis. So I'm going to redraw everything. Okay, I'm going to redraw everything. And then let me make it a little bit smaller. Hold on. Make it a little bit smaller. All right, so what I'm going to do now is I'm going to imagine visually what it would look like to rotate this region around the x-axis. I'm going to label my double arrow here, my curved arrow around the x-axis to kind of let everyone know I'm about to rotate around the x-axis. And I'm also going to draw an arbitrary rectangle in here and just make sure that it makes sense that as I move that rectangle left and right, the top and bottom functions are always the same, right? Red on top, green on bottom, the whole time, no matter where that rectangle is in that region. On the right-hand side, I'm going to redraw everything. I'm going to kind of label the red one on top, right? The blue one on the, or not, yeah, it is blue, sorry. Blue one on the bottom. I have the x-axis here, which also happens to be my axis of rotation. I am not going to draw the washer. If you want to, you can, you don't have to, all right? The most important thing to me right now is finding the outer radius and the inner radius. So the outer radius is the distance from the axis of rotation to the outer edge of the rectangle. So from here to here is R out. But because it's also the x-axis, right? It's also the height of the function f, right? That's also what f is.
That should be G.
Sorry, G. Thank you. The red is G. Oops, oh shit. Let me do it this way. G, thank you. This is the G function, right? So what is R out then?
X, root X.
Root X, right? That's what it is. It's the G function. And then my inner radius is the blue one, right? But the blue one is the F function. So my Rn is the blue one, which is X squared.
I have a question.
Uh-huh.
Is the red one G because it's on the top?
Yes.
Okay.
Well, the red one is G. Yeah, because it's on the top, just from the picture, it is. And when I'm looking for R out, I'm looking at the distance from the axis rotation to the outer edge. So if the outer edge is the red one, then that's what it is, right? That's what dictates it.
Okay, thank you.
Yep. Yeah, so that's why I don't want y'all to get like, I don't want y'all to like start thinking about this as a formula where it's like always going to be f of x squared minus g of x squared. Like that's not, it's that outer radius squared minus the inner radius squared. That's what you're going to use in the formula. So let me grab this again so we have it. Copy, paste it here. All right, so let's see, can you all handle this? I'm ready to put the integral together. I know I want to do an integral that's going to go from 0 to 1. And then it's going to be this formula replacing my R out, my Rn, and my H. Pi is a constant, right? It can come out. My outer radius squared. Okay, so here's my outer radius. My outer radius was square root of x, so I got to take square root of x and I'm going to square it, minus the inner radius squared. That's x squared squared. And then h is always going to be the thickness of that washer, which was dx. And that's something we should be very comfortable and happy to do. Integral pi, integral 0 to 1. If we square the square root, you just get x. And if we square x squared, we get x to the fourth. And I'm going to keep going because this integral is pretty straightforward, right? Pi, antiderivative of that is 1/2 x squared minus 1/5 x to the fifth. Evaluate that from 0 to 1. When I plug in 1, I just get 1/2 minus 1/5. And when I plug in 0, I get 0. Kills everything off. So this should be 3 pi over 10. So all I did there was get a common denominator between these two, right? That gives you 3/10 when you put those two together. And then I hit it with the pi, you get 3 pi over 10. So if you could take this region and rotate it around the x-axis, the volume of that solid will be 3 pi over 10. Now, I'm not able to tell you what the units are. Okay, it could be cubic feet, cubic inches, cubic millimeters. You know, it depends on the unit that you're measuring in. That's just the numerical value of the volume. Understand? Let's do the same thing, part B. Part B, I want to rotate around y equals -5. So I'm gonna take my picture again here. And rotate it around y equals -5 instead. So there's my picture. I'm going to need to come down here on the y-axis. I'm going to need to go down. Oh, I'm going to do a different color here. It might help if you draw your axis of rotation as a dotted line. You can do solid, doesn't matter. You just need to make sure you indicate that this is happening at -5. This is part B. We're rotating around y equals -5. So I'm going to come over here. I'm going to draw my rectangle. The red curve is on top. And just to be clear, I'm going to put square root of x so you know that. And then the blue one's on the bottom. That's your x squared. Your x-axis is here. Your axis of rotation is down here. And now let's figure out what r out is. All right, r out's going to be this distance all the way from here all the way down.
Wouldn't it be root x plus 5?
Root x plus 5. Because the distance from here to here is root x, and the distance from here to here is, well, 5 units. So 5. So root x plus 5. And then your r in, which is going to be the distance from the axis of rotation to the bottom edge or the inside edge, r in will be your x squared piece, and then again plus the 5 here. Got it?
Question,
Yes.
is it safe to say that the value at our axis of rotation, we're subtracting that value? Because I'd imagine that if our axis of rotation was above the 0 axis, we would be wanting to make it a negative, wouldn't we?
So I don't want to say anything like you just subtract the number, or you just add, you subtract the number if it's below, or you add the number if it's above. I don't want to say anything like that, because there are situations where maybe your region is down in the 4th quadrant.
Yeah.
And so things might be.
Things get weird.
It gets weird. So it's better to just look at it as a distance. Just to always look at it as a distance and try and figure out what that distance is.
So maybe
like
more so
visual.
think of it as taking the absolute value of it.
For in this case,
For
yes.
this instance, maybe, so just try to eyeball it. It's up to the situation.
Yeah, I would go case by case.
Okay,
Case by
gotcha.
case.
No, no.
Yeah.
Risky to take general rules.
Yeah, I
Gotcha.
don't want to generalize anything because there are situations where it could fall apart. So,
I understand.
all right, I'm going to set the integral up. My integral is going to go from 0 to 1 still. I'm still going to have a pi. And then it's going to be my outer radius squared, right? Outer radius squared. Well, my outer radius is the square root of x plus 5, but I have to square it, right? Square the entire thing. Minus, then I'm going to have my inner radius x squared plus 5, but then I have to square that, and then I can do dx. This integral is not as easy as the last one. Would you agree? Because you actually have to FOIL this out and FOIL this out, and you'd have a bunch of terms, and then you could do them term by term. But we could handle it. This is not any, there's no special, integration by parts, trig sub. We don't need any of that. It's just really just some algebra first and then crank it out. Yeah.
It would be tedious at worst.
It would be tedious. So I'm going to say plus dot, dot, dot. And remember last time I told you that what I'm going to do on a test is I'm going to ask you to actually find like the area of a few things all the way to the answer. But then after that, it's all about setup. On the exam, this would be the answer. You'd be done at that point. You've set it up. You've set up the actual formula that you need to calculate the volume. The rest is just computing, right? All right, let's do part C. So for part C, we want to rotate it around y equals positive 5 this time. So y equals positive 5. Let me squeeze that in here. So y equals positive 5 means we're going to be up here somewhere. Our axis of rotation is up above the region. We're rotating around this. Let me just give you a minute to catch up because I'm just copying and pasting and you're having to write things down. While you're doing that, try and set up the thing on the side. See if you can figure out R out and R in on your. I'm just going to refill real quick. Where's my pen? Oh, it's in my pocket. There we go. All right, I'm going to start drawing this. I'm going to start with my rectangle over here. I've got my g function on top. That's root x. I've got my f function on the bottom. That's my x squared. I've got my x-axis here. My axis of rotation is up here. Okay. R out is the distance from the axis of rotation to the outer edge of the rectangle. If you were standing there, right? Remember I said this is your head, you're standing there and you're looking out at that rectangle. you would see the blue is the outer edge, right? The blue is the outer edge. So you're looking at this distance from here to here as being your R out. What is it?
Be 5 minus x squared,
5 minus x squared. So how are you getting that?
because our distance from our total distance there is 5. And
That's
then
5
the
'cause
distance
you've gone
from,
up 5.
yeah, then our distance from the x-axis to x squared is, well, x squared.
There's x squared, right? So if you were to go from your axis of rotation all the way to the x-axis, that would have been 5. But then you want to take away this piece, which is x squared. What the hell is that noise? Oh, I know what it is. So your R out is the 5, take away the x squared. Who has a question on that? Anyone? Your R in is the distance from the axis of rotation to the inner edge of the rectangle. Ricardo, what do you think? What do you think for R in? Do you understand?
Yeah, I just did it differently. I added them instead of subtracting them.
Okay, so what would it be?
So for Fn is 5 minus root x.
5 minus root x, exactly. So we know the distance from here to here is root x. And we know the distance the entire way, right, was 5. So the Rn distance, which is just what's left here to here, that would be the 5, take away the root x. And that's it. Once you've got that, you're ready. You just put in the formula. Pi integral 0 to 1, the outer radius squared minus the inner radius squared dx equals ... whatever that equals. Okay. It's very visual. If you understand the visual part, I think, you know, it becomes pretty clean. But if you're having trouble with the visual, then of course it can be an issue. All right, let's do the last one, which was y equals 1, right? Want to rotate around y equals 1. So this part D around y equals 1. Well, y equals 1, I intentionally made y equals 1 because y equals 1 is actually just touching that top edge there. So your axis of rotation is just at that top right corner of the region. Doesn't make it any harder. It just makes, you know, it's got to be a little careful here. You've got your rectangle here. You've got your root x on top. You've got your x squared on the bottom. You've got your x-axis down here. You've got your axis of rotation, which is going to be slightly above this. From where I drew the rectangle, notice there's a little gap right here. So I'm just leaving a little gap. So let's see here. R out, I'm going to zoom in on this a little bit. R out is a distance from the axis of rotation to that edge right there. That's R out. In R in, shit, I can't even really see it in here, but it's this little distance right there from there to there. That's my R in. So we know that, let's see. Caitlin, do you want to help on this? Can you give me R out or an R in or one or the other or both, or do you need help?
I think I could be wrong, but R out will be like 1 minus x squared.
Good, 1 minus x squared. So the distance from the axis of rotation to the x-axis, that's 1, right? That's a terrible one. From here to here is 1. And we know from here to here is x squared. So R out will be take the 1 and subtract the x squared. Good. All right. Brandon, how are you doing with this? You understanding? What about R in then? I don't think we can hear you. It's okay if you can't unmute, that's all right. Arturo's ready to go.
Looks like he posted it in chat.
Oh, you did. Okay,
He
hold
says
on.
he doesn't have a mic.
Yeah. Yeah, 1 minus square root of x. Great. Okay. 1 minus root x. Very good. All right. And then now that's it. You set up the integral. We're done. Okay. Integral 0 to 1. You take the outer radius squared minus the inner radius squared dx. Bam. Okay.
You
Let
didn't
me
square your outer
reference-
radius.
I'm sorry. I forgot to square it. Yes, I did. Thank you. Let me go back to our notes here. Okay, these are the ones that are on Canvas for us. Maybe this will all make more sense now. If we're trying to do a solid revolution using the method of washers. Okay, so method of washers is all you know right now. Okay, there's another method called shells, and I'm going to introduce that in a minute. But whenever we're doing washers, the thing that lets you know you're going to use washers is when the rectangle that you draw, okay, see this rectangle here in yellow? When it is orthogonal to the axis of rotation. Orthogonal means perpendicular, okay? So our rectangle was perpendicular to our axis of rotation, we use washers. And in that event that we use washers, what we're going to do is draw this little thing, figure out what I call it RO instead of out, and RI instead of RN. All you're going to do is figure out what R out is, figure out what RN is, and then plug into the formula. And here I put here on the side, R out is the distance from the axis of rotation to the outer edge of the rectangle. RI or RN is the distance from the axis of rotation to the inner edge of the circle. That is something that's going to vary from problem to problem, right? Just depending on the way things are drawn and where your axis of rotation is, and if it's above or below or just touching the region. Your axis of rotation will never go through your region. Okay, it'll never go through your region because then you're rotating it on itself and it starts to lose meaning. So we just don't do that. Okay, everything we've done so far, I've given you two functions, f and g, that were functions of x, right? They were functions of x. But what if they're functions of y? And I want you to rotate around vertical lines instead. So what if your picture looks like this, right? You have like a left function and a right function, right? A left and a right. And we want to rotate this region around some axis, some vertical axis. Well, it's the same exact principle. Okay, but you're going to be sliding your rectangles or your washers up and down instead of left and right. So your integral is going to go, it's going to be pi integral from c to d. It'll be dy, not dx, but it's still r out, r in. Where r out is the distance from the axis of rotation, right? That distance right there, that's r out. And then this right here is r in. Does that make sense? That everything just gets changed over? All right. Let's do one of those. Okay, let's just do one of those. Find the volume of solid generated by rotating the region bounded by x equals y squared hold on, y squared, yeah, x equals y squared, and x equals, hold on a second. One half y, yeah, one half y. About part A, the y-axis. Part B, x equals -3, and part C, x equals 4. You've got to have a good picture in order for this to go anywhere, right? If your picture's wrong, it's going to be over. So x equals y squared. Everyone should know that that looks like a parabola that opens sideways to the right. Right, so we've got something like this.
I have a quick question, just for the sake of graphing them. Are we
Mhm.
allowed to use like something like Desmos? Obviously not on a
Well,
test,
Yeah,
but
not on a test, which is why I'd be
yeah,
hesitant to. Yeah, that's why I want you to get used to using your graphing calculator and using that parametric mode that I,
gotcha.
right?
Yeah.
Let's do something. Let's change the 1/2 y. Can we change it to 4y just to make our lives a little bit easier right now? Just change, you know what? No, make it 2y. Make it 2y. Sorry. Make it 2y. That way we'll have an easy solution to this. So x equals 2y is a line, and it goes through the origin, has a slope of 2, but in the other direction. So it's going to go like something like this. It's hard to see it like that. Boy, it's supposed to be a straight line. Oh, Jesus, that's terrible.
Professor, is it possible to just isolate x? So like, for example, like y squared, you have plus or minus the square root of x, which still look like the same thing. Would that be cool? Just so we can visually like draw it. Because I was having trouble with that last time.
Isolate the x.
So we
You mean
solve for x.
solve for y?
Yeah. Yes. Solve for
Yes,
y.
you could solve for y. But there might be a problem that you can't do that easily. Like that bonus problem that I gave y'all with the, whatever it was, sine y or whatever, like it may not be easy for you to do that. So
That one was a trip.
yeah, it's really better if you can get somewhat comfortable doing these. Yeah, let's continue. Do y'all want me to talk about the parametric mode on the calculator right now, or do you want me to just proceed here?
I'd found just proceeding. I need to just mess around with the calculator,
Yeah,
learn it.
yeah, because I
You
don't
can
know if
just
we'll have
YouTube
enough
it.
time. What's that, Lewis?
You can just send a real good YouTube video and like at the end of our day we'll watch it.
Yeah, or y'all could just look it up as well, using the parametric mode on calculator, right? Something like that.
That's what I meant. Yeah.
Oh yeah, no, I thought you meant me send it to you. All right, let's get to this. So look, my picture is actually not very good. It's gonna be hard for me to draw rectangles and stuff in here. So what I'm gonna do is I'm gonna say, okay, I get the general idea now. What I have is like X and Y. I basically have like a parabola over here like this. And then I've got some line that comes through. God, I cannot draw a straight line like that. I'm exaggerating things just to help me get a drawing. I'm supposed to take this region and rotate this around the, well, let's say part A, I want to go around the y-axis, which means my axis of rotation is here, right? Now, in order to use washers, my rectangle has to be orthogonal to this axis of rotation, which means that my rectangles have to go this way. All right. Remember, the green line is x equals 2y, and the red one is x equals y squared. I do need to know where they hit each other. And I need to know that as a y coordinate, not an x coordinate, because our integral, remember, is with respect to y, because everything is, these are functions of y, not functions of x. I can tell they hit at 0, and the other solution is 2. How would you get that? Set them equal to each other. You can visually see that 2 works here, right? But you could also just move the 2y over, factor, and you get 2 solutions. So this would give you y is 0, y is 2. All right, now I'm going to do what I did before. Remember how I drew the rectangle and I'm going to try to find R out, R in? I'm going to do the same thing, but everything is going to go up and down instead of left and right. In other words, I'm going to draw my y-axis here, my rectangle here, my green curves here, my red curves here. This is also my axis of rotation, right? And so R out is the distance from the axis of rotation to the outer edge. And my inner radius is the distance from here to here. But because my axis of rotation is the y-axis, isn't it just the R out is just the green function and the R in is just the red function? That's all they are, because my axis of rotation is actually the y-axis. So this should be the green one, which is 2y, and this one should be the red one, which was y squared. At that point, I can set the integral up. Pi, always going to be there, 0 to 2, outer function squared minus inner function squared dy. There it is. Is that too big of a leap? Is that okay the way I presented that? Y'all are all right with that?
This actually helped me switching
Okay.
it up.
Switching it? Okay. Let's now do the next one, part B, right? When we do part B, we've got this same picture. Well, we're going to change the axis of rotation. We're going to go around x is -3 now. So when I do that, I've got to get rid of this dotted line here. I'm not going to be able to. I'm just going to try and draw. Oops. Try and draw over it. There's my y-axis. And now we're doing part B, which is x is -3. So my axis of rotation is over here at -3. I've got a dotted line here. I'm rotating around this. So I'm going to draw my dotted line down here. I'm going to draw my y-axis here, draw my rectangle here, my red curve, my green curve, R out is that distance. R in is this distance. All right, let's hear from someone we haven't heard from. Who wants to volunteer R out for me? Anyone? Bueller?
I'll try it.
Okay,
Would R out be 2y plus 3?
2y plus 3, good. So from here to here, that's your 2y. And then this distance, you have to include that also. And so as an absolute value, like as a true distance, if you were measuring it, that would be 3. So your R out is 2y plus 3. Good. I think you understand it. So Jonathan, you want to give me R in as well?
Y squared plus 3.
Y squared plus 3. So from here to here is y squared, and then from here to here is 3. So you get y squared plus 3. There you go. And now we just go into the formula. Pi integral 0 to 2, right? We're going to go up and down with these things. The outer radius squared minus the inner radius squared dy, not dx, right? Where did I ask you to rotate it again? Ooh, x is 4. Yeah, x is 4. So x is 4 is a little tricky because x is 4 is actually right where they hit each other, right here. That's x is 4. How do I know that? Well, if I plug in 2 for y, right? If I plug in 2 for y, x is 4. So that's exactly where they hit each other in that edge point. So I'm going to start drawing this. Below, I've got my y-axis. I've got my axis of rotation. I've got my rectangle in here. I've got my red one here. I've got my green one here. I know the distance from here to here is 2y. I know the distance from here to here is y squared. R out is the distance from the axis of rotation to the outer edge of the rectangle, which is that distance right there. That's R out.
What was the axis on this one? It was 4?
4, I believe. Yeah, x is 4. Sorry, I didn't put it here. Part C, x is 4. I think that's what I put. Yeah, x is 4. So this is 4 right here. All right, new volunteer. Remember, the distance from here to here is 4. Right? Are y'all just being shy? Do you want me to call on you or?
Call on somebody.
I'll volunteer. I'll volunteer.
Go ahead, Eduardo.
It's gonna be 4 minus the y2, or sorry, y squared minus
There you
1.
go.
And it's gonna be 4 minus the 2y.
There you go. So it's the full distance, right? R out is the full distance 4, but you got to take away the y squared. And then the R in is the full distance, but you got to take away the 2y. And that's it. We're ready. Pi integral 0 to 2. Outer radius squared minus inner radius squared dy.
Does it need the secondary set of parentheses? Since the pie's on the outside now?
It's kind of implied. You mean like, could I
Yeah,
do
like
that?
those.
That's
it's
like
like,
yeah, that would be implied that this is all together in one integral, but you know, it's not wrong to have them. I would have them. I mean, just
Okay.
to be safe.
Yeah.
All right. Y'all doing all right with this? This section is just so involved. There's still so much more to do here. All right. I don't feel like I have enough time to start shells. it's just not quite enough time for shells. Plus, we can keep it as a completely different thought for next time. I think that'll be better. So why don't we do this instead? Instead of me moving into shells right now, for your homework, we're not done for the day. All right. But for the homework for 7-2, I would say try the 1 through 19 odd. But don't touch the 38 and 39 yet. Yeah. So for this, just don't do 38 or 39. Just try the 1 through 19 odd. And if you get them, then do the evens. That might be worth your time. Part of this is going to be the graphs. Can you graph these things properly? You can, use Desmos to help you, but you got to make sure that when it comes to the test, you're ready to graph something. So you got to be using your graphing calculator, whatever you need. You got to learn how to use it as a tool. All right, so here's what I'd like to do to finish this off in the last 12, 13 minutes. I would like for us to find the formula for the volume of a sphere of radius r. So we started class by finding the area of a circle of radius r, right? So we started class with. Now I'd like for us to find the formula for the volume of a sphere of radius r. How do you think I'm going to do this?
You're gonna get the area of a circle, or half of a circle, and then you're gonna rotate it about an axis.
Okay, yeah, so can't we take that same picture we started class with? Can't we take this same picture? Take that, you were saying take the whole top half, but would it be okay if I just take this blue region that we were working with earlier and rotate it around the x-axis? Right? Rotate
And then
around
we
the
could,
x-axis
then whatever that area is, double it to get the whole
and then
sphere,
double
right?
that answer, right? We can do that, yes.
Based.
Okay, let's try it. So if I come in here and I get my picture here, this is the function. Remember, we solved for that. It was y equals the square root of r squared minus x squared. Right, that was r there. So I'm not going through a lot of detail here because I did this earlier, right? If I want to rotate that around the x-axis, I need to see my rectangle in here. My rectangle is like this. Notice that the bottom edge of the rectangle is always touching the x-axis, right? Always, no matter where that rectangle is. That's a good thing, because when I draw my rectangle over here, the bottom edge is always touching the x-axis, which is actually the axis of rotation. The top edge, I'm going to do this one in red. The top edge is this curve here. So this top edge is the square root of r squared minus x squared, right? So r out is just that, isn't it? The outer radius is just distance from the axis of rotation to that edge. And what's r in?
Isn't it 0?
It's 0, right? There is the distance from the axis of rotation to the inner edge of the rectangle is always 0 because we're touching the x-axis the whole time, right? So there's no distance, there's 0 distance between that. Yeah? Okay, we have everything we need. We're going to do pi integral 0 to where?
R.
R, we did that earlier, right? R. And now check this out, this would be beautiful. We're going to take the outer function, right, which is the square root of r squared minus x squared, and do what with it? Square it.
Square.
minus the inner function, which was 0 squared dx. And isn't squaring that thing going to be nice for us? Because you're going to square the square root and it's going to go away. So you get 0 to r, integral 0 to r, pi times integral 0 r of just r squared minus x squared dx. Now we're ready for the antiderivative. No trig sub here. This is just a straight up derivative, antiderivative. Remember, r is a constant, so r squared is a constant, which means the antiderivative of r squared is just r squared x, right? If that was a 5, the antiderivative of 5 would be 5x. So the antiderivative of r squared is just r squared x minus 1/3 x cubed. And we're evaluating this from 0 to r. Which is pi. Now let's plug in r for x. If I plug in r right here, I get r cubed. Minus, and if I plug in r right here, I get 1/3 r cubed. And then what happens when we plug in 0 for x? Everything
Get
goes away,
0.
right?
Yeah.
Everything just goes away. So you just get pi times, let's see, r cubed minus 1/3 r cubed is
That'd be
2/3 r cubed. Which is really just, we could write this as 2 pi over 3 r cubed. Right? And that would be the volume. But remember, we only rotated half of it, right? We only rotated half of it. So when we rotated half of it, we got half the sphere. So we need to double the answer. So let's take this answer and let's multiply it times 2. And so the 2 hits the top there and you'll get 4 pi over 3 r cubed. 4/3 pi r, 4/3 pi r cubed. 4/3 pi r cubed, which is, if you go to your formula sheets, the volume of a sphere is 4/3 pi r cubed. Why? Well, we just showed why, right? That's pretty interesting, right? Like, it's harder to show the area of a circle is pi r squared than it is to show that the volume of a sphere is 4/3 pi r cubed. Because to do the area of a circle, you have to do trig sub. But to do the volume of the sphere, you only need basic antiderivative stuff. There's no technique of integration you need. It's actually pretty clean. You wouldn't think that, right? You would think it'd be much harder to show the volume of a sphere. It's not.
One of the questions that I have is like, is that how they originally found it, or they found it like a different way?
This is kind of like a chicken before the egg before the chicken question. I don't know what came first, if they had the formula and then just used calculus to verify it. There's a lot of different ways to do this, to show that the area of a circle is pi r squared and to show that the volume of the sphere is 4/3 pi r cubed. I think this is the most, like, for us and where we are in our math world, right? This is a pretty good illustration of how you can use integrals to do something general, like find the volume of something. Here's another one. I don't know if that answers your question, but I'm not sure what came first. How about this one though? I want to know if you have this object, which is called a frustum. Okay.
It's called a
This
lamp.
is, what's that?
It's a lamp head.
Yeah, it almost looks like a lamp shade. You know, if I tell you, okay, I give you the bottom radius, we'll call that R1. And I give you the top radius, we'll call that R2. And I tell you how tall this is, height, then what's the volume of this? We should be able to figure that out, right? I mean, like, there is a formula. Let me bring it up on, let me just Google search it. Volume of frustum. Oops. There it is. It's 1/3 pi times h times r1 squared plus r2 squared plus r1 times r2. What? How in the hell, right? Like, what did they do to get this, right? Well, can anybody think of how in the world you would do that?
Would you treat it
Rotate above an
as, what?
Rotate it around an axis.
Okay, so what are we
Center.
rotating now? What is it that you're going to rotate?
Weird four-sided square that's really slanty on one side. It would be, I can't draw for you.
Let me do it this way. I don't think, let me see here.
That shape.
How about
Rotated
if I
around the
had you think of
x-axis.
it this way instead? Okay, yeah, all right. So
Find the function for the side and then find the,
we have to
Fine.
start on a flat sheet of paper, right? And we're going to take some function and rotate it around the x-axis and get this. Isn't that just a line segment? It's just a straight line segment that goes like this. God, I cannot draw a straight line today. If I take that line segment and rotate that around the x-axis, isn't that going to be a frustum? Yeah. And do you know where you're going to integrate from? 0 to where?
the origin, x.
0 to h.
So 0 to here, but that should be this distance here, which we're just going to call arbitrarily h, yes? So I already know this. It's pi integral 0 to h. But now I need to know the r out and r in. Well, my rectangle is going to be like this, right? So what's r in?
0.
0, right? It's touching the x-axis the whole time. So all I need to really know is what's this outer function, but that's this line segment, right?
We can
Well-
find our slope by comparing the difference between the radiuses on the frustum.
You can, I think the easiest way to find the equation of that is to look at these as points. This is the point 0, r1, right? Because I told you the distance from here to here is r1. So that's the point 0, r1, and this is the point h, r2. I'm sorry, I got the r1 and r2s backwards. Sorry, I did the r2 on top. R2 here, r1. You understand what I'm doing here? I know I'm out of time. R1 is this distance right here. That's, sorry, R2 is that distance. So I just said, hey, just take this point, go up R2, that's the point. And then if you move over H and go up R1, that's this point. If you have 2 points, can you find me the equation of the line between 2 points? It's college algebra, right? First thing you do is you take the 2 points, you find the slope. The slope of the line would be the difference of the y coordinates over the difference of the x coordinates. Right? That's your slope. And now to find the equation, you use your point slope formula. Y minus y1 equals m times x minus x1. Y minus, I'm going to use this point right here. This is R2 equals the slope R1 minus R2 over H, and then times X because X1 is 0. So it's just X minus 0. If I solve for Y, this is the equation of that line. So that's the function. That's basically your R out. And then you integrate. You square that and integrate it. And that's where you'll get the formula from. I'm not going to go through the work.
That's badass.
Yeah. I mean, so you can just generate the formula. So any object that you can think of that you know, like even if you take a cone, right? A cone is actually an easier problem than this one. Because all you're doing there is you're just taking a line segment that goes from the origin out like that. And then this is H, and then this distance from here to here is the radius, which means this point is the point 0 or HR. And then you're doing the same thing. You find the equation and then just rotate around the x-axis. And if you did that, you would get the volume is 1/3 pi r squared H. Okay, we got to call it a day. Work on your homework, see how it goes today, Wednesday. That's it, right? So we don't see each other till next week. All right. Have a great day, everyone. I'm gonna jump
good
to my
weekend,
office
sir.
hours. Yep.
Bye.
Bye-bye.
Yeah, I have a question about 6.6, the homework that we held off on until like after spring break.
Yeah. Okay.
Is that due this weekend still? Because I
Yeah,
don't think there was.
turn it in with the next assignment you turn in.
Gotcha. Yeah, I was just looking through the like when stuff was due, and I was like, oh yeah, wait, we're still at 6.6, and I was like halfway done with it.
Yeah, no, yeah, because the timing on that, we just didn't get through it before the spring break. So
Gotcha.
turn in with your other stuff.
Gotcha. All right, I'll see you next week.
Okay.
Sir, were you able to look at the bonus question I sent you?
I
just wanna know
haven't.
if
I had a few students send me it. I haven't looked at it yet.
Okay,
If you want, I'm gonna jump to my office hours. You can come in there and I can look at it, but it's
Sure.
only if you have time right now.
I don't mind, yeah.
Yeah, okay. I'll jump over there. I'll meet you there.
Sounds good.